In this presentation, we are going to look at Lagrangian optimization. So here is the problem here. What is the maximum of the expression 5x plus 2x squared plus 4y subject to the constraint that 2x plus y is equal to 20? So what we're going to do is use Lagrangian optimization. First off, what we're going to do is let the function f of x let it equal that f of xy is equal to 5x plus 2x squared plus y, and this expression here g of x and y, we're going to, the expression was 2x, the constraint was 2x plus y equals 20. What I'm just doing here is re-expressing that as 2x plus y minus 20 equal to 0. We just need it in that form for constructing this expression g of x. So the Lagrangian therefore is this, and what we're going to do is multiply g of x and y by this term here, lambda, and that's going to be part of our expression as we go forward. So essentially what we have here is L, I'm just going to leave out the arguments, that is equal to 5x plus 2x squared plus 4y minus lambda times 2x plus y minus 20. Okay, and just like sort of simplifying that, we could say 5x plus 2x squared plus 4y minus 2 lambda x minus lambda y plus 20 lambda. Okay, so essentially what we're going to do is that expression there, what we are going to do, there it is again. I've just put everything together. I have the x terms here together and the y terms here together, but more or less it's the same as what I've just done in the last slide. What we're going to do is this expression here, we're going to differentiate it with respect to x. We're going to differentiate it with respect to y. And we're going to differentiate it with respect to lambda. Okay. So we got three differentiations to carry out. So differentiated there with respect to x, y, and lambda. So the first one is differentiate that with respect to x. So this here and this here, those are part terms there. They don't have any components in x, so we can just disregard that entirely. This part here is a constant as far as x is concerned. So we're just gonna, that is simply 5 minus 2 lambda. This term here for 2x squared, differentiating that with respect to x, we get plus 4x. That's it. Yep. So that's the first part of our expression. That's the first expression we have to collect. So let's have a double check that. There it is again. There, I just slightly rearranged from the way I've done it on the last slide, but there we go. So with respect to y now, L with respect to y. Again, we go through it here and we sort of see that there's nothing here with respect to y. So it's just this term here. It's 4 minus lambda times y. So simply 4 minus lambda. Straightforward enough in that case. And moving on. So with respect to lambda, so I'm just going to rewrite it out in terms of lambda. I'm just going to extract the lambda terms out. We can disregard everything else. 2 lambda x minus lambda y plus 20 lambda. Okay. And so we have minus 2x. So we're differentiating these terms now with respect to lambda. Minus y plus 20. There we go. So these are the three expressions we've collected up. with respect differentiating with respect to x, with respect to y, and with respect to lambda. What I'm going to do now is let all of these expressions equal to 0. So all of these, this is a part of the finding the maximum, letting the differentials equal to 0. So 5 plus 4x minus 2 lambda equals 0, 4 minus lambda equals 0, minus 2x minus y plus 20 equal to 0. Straight off, what I'm going to do here is we can spot that lambda necessarily is equal to 4, based on this one here. And not necessary but useful is, I'm just going to rewrite that. I'm going to just change the sign of that just to make it easier to deal with. So lambda is equal to 4. That's a sort of immediate step that we can take. Now, I'm going to sort of make a remark on that up here. So we've just found that in the last case slide, lambda is equal to 4. So what does that mean for this first expression up here? Well, we have 5 plus 4x minus 8, that's 2 times lambda, 2 times 4, equal to 0. So 4x minus 3, 5 minus 8 is equal to 0. 4x is equal to 3, x is equal to 3/4, or let's call that 0.75. Okay, that's a big step there. So we know what lambda is equal to, 4. Now we know what x is equal to, 0.75. Okay, that is going to help us with this one here, because we already know what x is, and we just need to sort of compute what y is. So uh, 2 times 0.75 plus y minus 20 equal to 0. So 1.5 plus y is equal to 20, just bringing the 20 on the other side. Subtract 1.5 from both sides, we get y equals 18.5. So now we know x, y, and lambda. Y is 18.5. So that's them all there. We're not particularly interested in lambda, we're particularly interested in x and y. And the constrained maximum is at x equals 0.75, y equals 18.5. So what we're going to do is we are going to compute, find out the maximum of that expression subject to that constraint. So essentially what we have to do now, this is the original question here. What we have to do now is simply evaluate the expression, this expression here, at x equals 0.75, y equals 18.5. So let's do that. That's 5 times 0.75 plus 2 times 0.75 squared plus 4 times 18.5. That's a bit of calculator work. You should find the answer to be 78.875. And so that is the maximum subject to that constraint. It's the maximum of that expression subject to that constraint. So that pretty much wraps up what we have to do. There we have it again. Evaluate the function at 0. This function up here. Even I'll just make that a bit clearer. We call that f of x, y earlier on. So evaluate that function at 0.75, 18.5. In this presentation, we are going to look at isomorphic graphs. Now, in particular, what we're going to consider is the matter of, I just have to scroll back here. Two graphs can appear very different when inspected visually, but they could have the same adjacency structure, which is to say they could be isomorphic. But you have to sort of inspect the graph thoroughly before you can make any decision. So here we have two graphs, and in each case what we're going to do first off is just write in the degree for each vertex. So that's degree 1, degree 3, that's degree 2, that's degree 2, that's degree 2. And in graph 2, this is degree 1, this is degree 3, this is degree 2, 2, and 2. So we're going to start off. What is always useful is to start off with the graph with the degrees, the vertices with the highest degree. So in this case, I'm going to pick out E and R. Okay. Now let's just see what the degrees of the vertices they are connected to. Well, 1 in this direction, 2 in this direction, 2 in this direction. And here, 2, 1, and 2. So far, so good. Now, actually, if you had, these are two very simple graphs, but if you had a problem here, for example, this didn't work out, but there was another vertex of degree 3, just switch that instead and keep going. So, so far, so good. So what we're going to do is assign equivalence, or like the sort of try and construct an equivalence. So we're saying T is equivalent to A in the other graph. We're saying that this is equivalent to E in the other graph. We're going to just have to sort of take a pot shot here and say that, or take a lucky guess and say that this top one here, this is going to be equivalent to C, and this one down here, that is going to be equivalent to D. Okay, and what? Let's just look at these now. So A pretty much is A and T. They're both of degree 1, so not particularly interesting. So we're going to move to the other two. So S, it's connected to a vertex of degree 3 and a vertex of degree 2. Let's go to D on the other side. It's connected to a vertex of degree 3 and a vertex of degree 2. So far, so good. And so what about the other one? Likewise here, vertex C is connected to a vertex of degree 2 and a vertex of degree 3. And like the last one, the odd man out now is B, and that must equal to Q. It is connected to a vertex of degree 2 and a vertex of degree 2. So that everything checks out now. So what we're saying is the isomorphism is as follows. A corresponds to T, B corresponds to Q, C corresponds to P, D corresponds to S, and E corresponds to R. Okay. Anyway, that's the general gist of it. Now, I'm just going to add in one extra other remark. So that's one approach we can take. But we're also going to look here at cycles. So we actually have a cycle of length 4 here. Okay. That's a cycle of length 4 there. And it's the only cycle in that graph. And is there something that corresponds to it here? Well, yes, there is. Going down here, up here, and up here. There is another cycle of degree 4. And in this case, there is only one cycle, of length 4. And in both graphs, there is only one cycle, and it is both. They are both of length 4. So that's another way of checking. There's quite a few ways of checking if graphs are isomorphic. Anyway, that ends our presentation.